Okay, so thanks a lot for having me. I will be talking a bit about intrinsic self-supervision for data quality audits. My name is Fabian Gröger. I'm a second year PhD student at the University of Basel. So in this presentation, it's all about data cleaning. So as Jimmy already said, like Voxel 51 is also a tool for like doing some sort of data curation, and we follow a very similar line. So the idea of data cleaning, data curation, whatever you want to call it, is that you have any sort of, say here, imaging data set. And the goal is to find any inaccuracies in it. And for example, in this data set and in our paper, we were particularly interested in three types of issues, namely off-topic samples, which are samples likely included by mistake, near duplicates, which are pairs of samples containing different views of the same object, and label errors, which are samples with the wrong class label. And of course, if we think about all of these data quality issues, then they are highly dependent on the data set. So for example, in a data set full of emojis, the emojis, an emoji about the chainsaw wouldn't be considered an off-topic sample. But here, since it's all natural images, it is considered a off-topic sample, meaning that if you want to solve the task of data curation or data cleaning or data quality audits, then it's very important to understand the context of your dataset first, which makes this whole task extremely challenging. And if we think about, or if we turn towards a bit more a challenging data set, so for example, a medical imaging data set, where we not only need to understand the content of the data set itself, but also understand a bit or have a bit of domain knowledge, then this whole thing becomes even more tricky. Because in this data set, which is a data set, for example, for chest x-rays and spine x-rays, it's way more tricky to find, for example, an off-topic sample, which is here a X-ray of a knee, which shouldn't be in there, or a near duplicate where since it's a very standardized setting, it's even more difficult to find these sort of near duplicates. And the same also holds for label errors. So we can already see that this task is quite challenging and very dependent on the context itself. And if we want to motivate this whole data cleaning and data curation a bit more, then we can think about that we probably all know that training and evaluation data can indeed be very messy. We see this all over the place, even in like academic benchmarks, in industry application, or just in real world data. It is very messy. And for a long time, if we look towards more traditional data clean or traditional machine learning, then we can see that for a long time, data cleaning has been essential for the whole pipeline. So in traditional machine learning, a lot of research was invested into actually doing data curation before even fitting or training any sort of algorithm. And when we switch towards deep learning and this area of deep learning, we saw that these models tend to work quite well, even when they are subject to quite a lot of noise. And even if we have a bit of noisy data, we can just scale up this whole data and then we can work with the noisy data even more. But this whole argument is solely based on noise, which is only affecting the training set. So that's why even in this setting, like all of the noisy, learning from noisy data is very, very an interesting and a growing field, but it can't really cope with the fact that you have noisy evaluation sets. Because if you have noise in the evaluation set, then it can lead to inconsistent performance estimates. So, for example, if we think about some sort of algorithm and we have an messy evaluation set, then we don't really know if the performance improvement or the performance difference is actually due to the model being able to learn or generalize better, or because it's just better at actually remembering noise or predicting noise. So that's why it's very important to also look at this. And if we look at what is currently being done for data cleaning, then we can see that in most of the applications, it's still manually performing data cleaning. And for evaluation data, typically one looks at the small sample of the evaluation data and does some sort of manual data cleaning. But even in this very, very restricted set, if we look at a few hundred samples, it's already very time consuming, very labor intensive, and very error prone. So for example, if we just consider the 3 data quality issues that I've shown so far, so off-topic samples, near duplicates, and label errors, then we can think about that just detecting, for example, near duplicates would require to compare every possible pair in the data set, which is already infeasible for very small scales. So that's why it's very often error prone, suboptimal, and for a lot of practitioners, be it researchers, be it more industrial data scientists, it's often the least enjoyable task. So that's why we need a new solution, and that's where this whole project comes in. So the main goal of this project was to reliably create a methodology that is able to detect these data quality issues, such as off-topic samples, near duplicates, and label errors, and that without introducing any significant biases again. And the reason why we wanted to emphasize this without introducing significant biases is that if you, for example, do some sort of automatic data curation, then you might well solve a bit of the issues with the data quality issues, but on the other hand, you might again introduce some new biases, some cleaning biases, because you remove minority groups from your data set, which are then again suboptimal. So that's why instead of doing something fully automatic or having a fully automatic methodology, we wanted to really emphasize on a human AI collaboration so that our methodology is intended to be used in this collaborative way. And for this to actually have a positive influence, we wanted that the methodology compared with a human actually reduces the time needed for finding these data quality issues. So that was one of our main goals. And the last one was also that we wanted to investigate how this all looks like and if it's actually a real problem in existing benchmark data sets, and what are the influence, or what is the influence of these issues on the training and evaluation. So in our project, or in our paper, we made 3 findings. First, that self-supervised learned representations can indeed be used to find data quality issues. So we quickly found that certain regions or combinations of different relationships in the representation space actually enables us to find data quality issues. And to solve this whole issue of context-aware data quality issues, we created what we so-called like context-aware self-supervised representations, which just means that you train your self-supervised algorithm on the data set that you actually want to clean. And even though self-supervised learning is typically intended to be used with much larger data sets, we were able to make experiments and show that this works when going to as few samples as a few hundred samples. And that means that even if the representations which are learned with self-supervised learning are globally suboptimal, so if you would fit a linear layer on those representations, they would be pretty bad. But the local consistency of these representations are still being able to be very useful and can be exploited to find these data quality issues. And the last one was that the combination of self-supervised learning and distance-based indicator functions we were able to find quality issues. And by putting all of those things together, we created a new methodology, which we called SelfClean, which enables us to find these data quality issues. And the basic idea of SelfClean is that you start with some sort of noisy data set that you actually want to find data quality issues within it. And then you start by training a self-supervised encoder on this data set. And in our paper, we compared different kinds of self-supervised strategies and found, for example, that a multi-crop objective such as Dino is the one which tends to work the best across all of our experiments. And once you have these representations, which are here illustrated in the middle, then it can be exploited by using some distance-based indicator functions for each of the three issue types separately. So for example, to find off-topic samples, we can use single linkage agglomerative clustering, and which then produces a ranking on which we will then later see a bit more in detail. And for near duplicates, we rely on pairwise distances. And for label errors, we rely on intra-extra class distance ratio. And that just means that you measure the distance from one point to the nearest point of the same label versus the point to the distance to a point of any other label. And the idea of our whole methodology, and because we emphasize on this human AI collaboration, we emphasize that we should model data cleaning as a ranking problem rather than a prediction problem. Because if we, for example, look at related work in the label error domain, then we can see that it's typically modeled as a binary prediction task where it's either true or false that a certain sample is a label error. We instead really look at it as a ranking problem where samples appearing earlier in this ranking are more likely to resemble a data quality issue. And of course, a ranking can be derived from any score, which, for example, these distance-based functions produce. And our methodology works in two different operational modes. The first one is the human in the loop one, which is the one which should be used when wanting to clean anything. So the idea is that you run self-clean, it produces these rankings for each of the three data quality issues. And then you can simply annotate along these rankings, which are now informed. So you will more likely see data quality issues in the earlier rankings. And then as time progresses, or as you progress over the ranking, you will see more and more valid samples. And then after you see a certain number of consecutive negative responses, you can then, for example, then just stop annotating and consider the rest as, for example, clean. Of course, there's always a remaining probability that after a lot of samples, there's still a data quality issue, but this is pretty low after you see a very long number of consecutive negative responses. And at the same time, we also still wanted to make our methodology compatible by creating a fully automatic mode, because even in this very modest regime or work of data curation, data cleaning, we can see that most methodologies really are intended to be used in a fully automatic way, which we sort of go into a different direction, but we still wanted to make our methodology compatible with that setting. We, however, emphasize that this methodology or this mode should be used solely to estimate a data contamination and not for performing a automatic cleaning. And we also define the fully automatic mode a bit more differently than others, because related work simply sets a hard threshold at a certain value, which is, of course, very like you need to engineer this threshold quite a bit. You also need to find a bit where this optimal threshold lies. It's usually not generalizable if you add a bit more data, if you change the data quality issue type, and it also doesn't generalize across data sets. So it's a tricky thing to optimize. And we instead take a bit of a different approach where we estimate how the normal distribution of the scores here, for example, in green, looks like and how it sort of diminishes. And we then try to estimate or try to fit a distribution over this diminishing and see where this bound gets invalidated and consider those samples which invalidate this bound as the abnormal samples, which is a bit more robust to the data set and to the issue types which we are investigating. So we have now talked quite a bit about the methodology that we've introduced, but we also needed to evaluate that. And if we look at what is being done in sort of related fields, then we can see that there are two main strategies. The first one being a synthetic evaluation, where we actually take existing benchmark datasets and you synthetically inject some noise which you want to then detect. So for example, if we consider off-topic samples, then this is, for example, done by adding some sort of samples from other modalities, by taking existing samples and corrupting them quite a bit, or for near duplicates by creating some sort of augmentation strategies to create the different views of the same object, and for label errors by changing the label according at random or according to the distribution of the class itself. And as a second evaluation, we also compared our ranking and the scores that we obtained from SelfClean against, for example, some metadata which is available. So for example, a lot of medical imaging data sets contain information about which patients, which lesion are the same, which can then be used as sort of an indication for near duplicates. Some of the existing benchmark datasets contain a small sample of annotations for example, label errors, which we can also use. And if we look at some of the results from our paper, then we can see that, for example, here for the synthetic evaluation, where we can see on the x-axis the contamination that we can actually sort of influence and control, and here the three different types of data quality issues for three different benchmark or seed data sets. Then we can see that our methodology, which is shown here in deep green, is significantly outperforming all the other methodologies. And we also compared how these different kinds of related or competing methods would work if we would give them the context-aware representations, which are always the ones which are filled out, instead of the ones which are not filled out are the ones which are general ImageNet, for example, representations, which are not context dependent. And we can see that there is really this significant gap between our methodology across contamination rates, across data quality issue types, with one exception, and that is sort of this one here. And some of you might have already seen or read on the slide before that one of the biggest assumptions of this whole evaluation is that the seed data sets, on those that we are actually relying on, need to be clean. And because otherwise, if we inject some noise and we look at the data quality issues or evaluate the data quality issues, then our methodology is maybe suboptimal, although it would find the real contamination, which is just not in the synthetic ones, or is not ranking the synthetic ones prior to the real ones. And that is actually the case for this data set here, and that's why this is sort of a bit weird. And if we look at the natural contamination, where we, for example, compare against the metadata of same lesion, same patient, same person even, or verified label errors, then we can see a similar picture as before, where our methodology is again significantly outperforming its competing methodologies. And as we said, or as I said, in the goals of this project, one of the biggest things was that we also wanted to see if this is indeed a real problem in sort of academic benchmark data sets. And we found this indeed to be the case. So we looked at many different benchmark data sets, be it medical imaging benchmarks from diverse domains such as dermatology, radiology, histopathology, but also for general images. And we saw that we are still able to find or estimated the contamination of these data sets, to some of them quite high. And we can already think that if these data sets are being used in papers in academic publications and the progress of our whole field is measured by these data sets and benchmarks, then of course this has a significant influence. And if we look at how these issues actually look like, then, for example, here it's shown for ImageNet, then this is the top 15 ranking for near duplicates, for the off-topic samples, and for the label errors. Then, for example, we can see that here we can see almost the exact duplicates. When we go a bit further along, we can see more near duplicates. And what is interesting about these samples is that even though some of them might look like exact duplicates, they're usually being able to be traced back to different kinds of resolutions, which stem from sort of thumbnail images, which are very tricky to detect with traditional methodologies. And on the other hand, off-topic samples show some of more samples which are more outside of the distribution of the things which one would expect in ImageNet. And the same goes for label errors, where we see, for example, near duplicates, where both of the samples are assigned to different classes. And the same also holds for medical imaging datasets. So for example, here on the left-hand side for dermatology, here for radiology, where for near duplicates, on the left-hand side, we can see a lot of near duplicates or exact duplicates. We can see some samples which are likely included by mistake. And here for the radiology data set also, where we can see some device malfunctions and also device malfunctions with positive labels. And we then turned a bit our attention towards how this whole these samples actually influence, or these data quality issues actually influence the evaluation itself. And for some of these data sets, we performed the cleaning and we looked at how the evaluation performance looks, for example, different if we solely clean the evaluation set or if we clean the evaluation and training set. And we can see that for here, in this case, very simple models, we can see that the evaluation set cleaning almost always, with only 2 exceptions, had a significant influence. And if we look at the influence on the training set, then on the other hand, we can see that there is again this trend that it has an influence, but this influence here is most always a bit of a positive influence. And the reason for this discrepancy between either a positive or negative influence versus a more solely positive influence for cleaning solely the training set is that if we think about the label errors before, for example, in ImageNet, where we have near duplicates assigned to two different labels, then this, of course, poisons the optimization process of a model. Whereas if we have an evaluation set which will get cleaned or a leakage of a train test leakage, then we can see that this has either a positive or a negative influence, depending on the distribution of the near duplicates versus off-topic samples versus label errors. But we can really see that there is a significant influence if we can actually remove those issues, which of course raises a lot of question about the validity of today's benchmark datasets. And we then also wanted to see if the ranking which we produce actually aligns with what a human understands about the task of data cleaning. And that's why we also, for some of the data sets, performed this human assessment where we've took the lowest part of the ranking, showed it to human annotators, and asked them sort of about their assessment of these data quality issues. The same being done also for a random sample, and saw that it, in most of the cases, actually aligns with the understanding of what a human considers the task of data cleaning or these data quality issues to be. And last but not least, we also, because we emphasize on this human AI collaboration, one of the major things that we wanted to quantify is the amount of inspection effort that can be sort of reduced by using SelfClean. Because you have what is currently being done, which is manually doing the data cleaning, which is a purely uninformed data cleaning without any algorithmic help. And you have SelfClean. And now we wanted to see how does this collaboration actually benefit. And the way that we actually measure this is that we look at the number of samples which are needed to find for a certain recall. So to find, for example, 10 data quality issues, how many samples do you need to annotate with the SelfClean informed ranking versus the purely uninformed ranking? And we can see here again in green the SelfClean one. And we can see that compared to its competitors, it's again significantly better. And for example, here near duplicates, it can reduce the inspection effort even up to a factor of 50. So, which is a extremely, like, it's a very big reduction by purely using this informed ranking from SelfClean. And with that, I want to thank you all for your attention and give it a try. So using SelfClean is quite easy. So it's just pip install SelfClean and then you can run it on your dataset. It's an algorithmic, it's an academic way of, or it's still an academic pip package. So it's very rudimentary. But yes, give it a try. And if there is one thing I would like you to remember from my talk, it's really that data curation, data cleaning, or data inspection does not always need to be very cumbersome. It can be actually quite fun if you use the correct tools.